Hooke's law data analysis. And it also gets me into something that is kind of one of my bugaboos with the way we talk about Hooke's law in physics. All right, so let's set up an ideal version of Hooke's law data collection. All right. So what did we do in Hooke's law? What was the first thing that we started with? Yeah, well, before we did that, we actually had this, I don't know what you want to call it, a fixed ceiling to which we attached a extension spring. So this thing is going to be called an extension spring. Do you know what an extension spring is? Yeah, it's a spring that exerts force when you go like this. Do you know what a compression spring is? If I try to push the compression spring together, it pushes away from that. Those are different. There are some springs that act in both paradigms, that act both as a compression and an extension spring.
So would an extension spring not move if you compress it?
Someday, I would love you to come to my office and to play. This is a non-trivial problem. This is the difference between applied and pure math. Pure mathematicians don't care about this. In a pure mathematics course, you could say all springs are both extensions and compression springs. No problem, right? If you actually took that spring, those springs there, in their resting state, they're more cylinders than they are springs if you push inward. I mean, they're literally just solid objects. They do not satisfy Hooke's law if you push them in the right position because there's no give there.
They're already touching, right?
They're already touching. Their coils are touching. They're wrapped fully tight, right? So the only way that the extension spring acts properly is to actually pull it away. And there's some really interesting stuff that comes up from this if you're actually designing systems with that. And it has to do with where you impose zeros, which is quite a satisfying dilemma for a few weeks of thought. All right, so let's do what we said our first measurement. What was the first measurement that we made?
Initial.
Yeah, how much mass did we put on for the first entry? M1 was equal to 0. And then what did we do? Yeah, we measured this thing. And in our case, we actually said that I'm going to do this. I'm going to impose that positive positions mark in the downward direction. So my 0 position, I might call this x equals 0 position right up there. Right? And then earth ground is down here, but this is what we call ruler ground. Right? And so you know that that's going there. What was the next measurement? Yeah, so what did we do? All right, so we have this thing, we attach a mass to it, the spring extends a little bit because it's now in the extension paradigm. And then what do? We mark the position of this thing. Okay, so there is a claim here. The claim that I'm going to make is the moment I drop this mass, there is now a force acting in the exact downward direction. Right? What force is that? It's the mass times the acceleration due to gravity. So this is 9.8 times m2. If the acceleration of the mass, so I don't know what you want to call this, but if this mass is not moving, what does that mean? There's also, it must mean that there's an equivalent force going upwards, and these two forces together cancel out. All right, so you might call this the force of the spring, and then the claim would be that the force due to gravity for mass 2 plus the force stored in the spring for mass 2 together equal to 0. Well, what would that mean immediately? Yeah, well, together, the whole claim is this is going to be the sum of the forces acting on that mass, because you're literally just taking the net forces there, right? Well, what does Newton's second law tell you? The sum of forces is equal to the mass that you're focusing on times the acceleration of the mass itself. But if the thing is at rest, what do you know about acceleration? If mass, no move, A equals 0, no acceleration. Okay, so what does that immediately mean? That the force of gravity is opposite to the force of internally stored in the spring, right? Yep.
From a physics standpoint, it doesn't make sense for acceleration to ever be 0 because gravity is always affecting the mass.
Yeah, be careful. I'm not asking what the acceleration due to gravity is. I'm asking if you track this thing using a displacement function and you let this thing settle down, what is the second derivative of that displacement function? So that's a different problem, right? Yeah. Okay. All right, so let's do, well, I guess we could actually just iterate it from here. Does this have to be mass 2? No, we actually could do this for all masses x or m sub I, where I ran from, in this case, 2, I think we went all the way down to like 40. In that data set that we saw on the board, I think I did 40 different measurements. So the vector was 41 by 1, because the first entry was 0, right? Okay, so in this case we would say that every single one of those entries looks something like this. Okay, all right, so we're not done yet. We're going to go back over to that board. And I need my notes. If I teach this class every quarter, I don't have to look at my notes anymore, but I've not taught this class for 2 years, and so it's been a while since I thought about this stuff. Okay. All right, so let's think about how we could set up a Hooke's law experiment and how the actual additions and subtractions come out. So the claim was we had this mass matrix, or mass vector, I'm sorry, m1, m2, all the way down to mn, where n is the number of measurements that we collected. So that's called the mass vector. From that mass vector, my claim is that we can actually calculate a set of forces. So now we can have what we call a force vector generated by those masses. Could you guess what the force vector is? It would be 9.8 times m1, 9.8 times m2, all the way down to 9.8 times mn. Well, what's that? It's 9.8 times m1, m2, all the way down to mn, and that's just 9.8 times the vector m. Each of those masses ended up producing a position vector, or excuse me, each of those masses ended up producing a coefficient, which was the position of the movable end of the mass, or the movable end of the spring along my ruler, right? Okay, so then we said let x be equal to x1, x2, all the way down to xn be the corresponding position of movable end of spring, which implies, what if I wanted to figure out how far the mass moved the end of the spring from the starting position to the ending position? What would I do there if I was looking for the displacement of the movable end of the spring? Yeah, perhaps I say that the u would be equal to, well, let's see. The first one would have moved x1 minus, yeah, we're going to say that x naught is the value of the end of the spring under no mass. If my first data position is equal to the scenario where no mass was attached, this would be 0, right? But this is sufficiently general to allow that my first data collection doesn't have to be the case where I measure the end of the spring with no mass on it, right? Okay, what's the next one? x2 minus x0. Next one would be x3 minus x0, all the way down to, okay, do you see a vector addition problem? What is this now? x1, x2, all the way down to xn minus x naught times a bunch of 1s, right? Okay, and then maybe we want to be a little bit lazy and say that this is going to be minus the initial position times the 1 vector, where that 1 vector is the same size as the x vector. Yep.
Is it an addition problem because it's like...
Yeah, you can always turn this into, you are correct, that you can always say to yourself that this is actually xn times 1 plus negative x naught, which is a scalar, times that thing, right? Or if you were really excited, you could, I don't know what you want to call that vector, you could call the vector n is equal to negative vector 1, right? So could you guess what that is? It's a vector with n coefficients, each of which is equal to negative 1 in this case, right? So now this thing right here is a scalar vector multiplication, and that gives you the displacement of that particular vector, right? And now all of a sudden, if we wanted to study how forces correlated with displacements, I could now graph force on one axis, displacement on another axis, and do you know what Hooke found? Yeah, that the force stored in the spring was linearly correlated with the displacement achieved by that force, or the displacement measured associated with that force.